Look at this aircraft. This is the A-4 Skyhawk, one of the most perfectly proportioned, aerodynamically elegant attack jets ever designed for the United States Navy. Every curve, every angle, every millimeter of this airframe was obsessed over to reduce weight and maximize efficiency. It is a masterpiece of minimalist aerospace engineering. Now look at this one. This is the Israeli version, the A-4 Ayit. Look closely at the back. Protruding from the engine exhaust is a blunt, unaerodynamic metal tube extending past the tail. It looks like a mistake. It looks like something a maintenance crew accidentally left bolted on before takeoff. It looks like industrial plumbing grafted onto a precision weapon. Why would one of the most battle-hardened, technically sophisticated air forces on Earth intentionally degrade the aerodynamics of their primary strike aircraft? The answer is not an engine upgrade. It is not a thrust modification. That ugly piece of metal was a decoy, a trap built to die so the pilot wouldn't have to. In October 1973, Israel's Air Force was being torn apart by a Soviet weapon so cheap and so simple it almost defies belief. They didn't have years to engineer a new jet. They didn't have billions of dollars to build a new defense system. The solution they came up with cost less than $100, looked like it came from a hardware store, and saved dozens of pilots' lives within days of being installed. This is the story of the blue-collar bomber that carried the weight of a nation, the missile that almost wiped it out, and the piece of steel pipe that stopped it. To understand why the Skyhawk was so critical to Israel and why losing it was so catastrophic, you have to understand the genius of the man who built it. In the early 1950s, the U.S. Navy issued a specification for a new jet-powered attack aircraft. It needed to carry a 2,000-pound bomb, fly at 500 miles per hour, and come in under a maximum weight of 30,000 pounds. Most aerospace contractors looked at that specification and told the Navy it was borderline impossible. The performance requirements were too demanding for the weight limit. Ed Heinemann, chief engineer at Douglas Aircraft, didn't just meet the requirement, he demolished it. His Skyhawk came in at just over 9,000 pounds empty, less than a third of the Navy's weight ceiling. He achieved this through obsessive, ruthless engineering discipline. He questioned every component. He eliminated every gram of unnecessary structure. The wing was designed as a single continuous delta shape, so thin and so stiff that it didn't even need to fold to fit on an aircraft carrier elevator, which was unheard of for a carrier-based jet. They called it Heinemann's hot rod. It was fast, it was tough, and it was cheap to build and cheap to maintain. When Israel began purchasing American jets in the late 1960s, the Skyhawk was a natural fit. They eventually operated over 200 of them. In the Israeli Air Force, the F-4 Phantom and the Mirage 3 were the glamorous machines, the dogfighters, the interceptors, the jets that shot down MiGs at altitude and made headlines. The A-4 had a different job entirely. Unglamorous, dangerous, essential. Its mission was close air support and ground attack. It flew low, below radar, below cloud cover, directly over advancing enemy armor. It absorbed anti-aircraft fire. It dropped iron bombs on tank columns and pulled away before the blast. They called this kind of flying mud moving. And in the war that was coming, the mud movers were going to be Israel's first and most critical line of defense. But there was a problem buried in Heinemann's brilliant design, one that nobody fully appreciated until the shooting started. And that problem had a very specific, very deadly shape.
October 6, 1973, Yom Kippur, the holiest day in the Jewish calendar. While most of Israel was at synagogue or fasting at home, a coordinated assault of staggering scale hit the country on two simultaneous fronts. In the south, Egyptian forces crossed the Suez Canal in overwhelming numbers, punching through the Bar-Lev defensive line with armor and infantry. In the north, Syrian tank divisions rolled into the Golan Heights. Israel's ground forces were outnumbered, outgunned, and caught completely off guard. The Israeli Air Force was supposed to be the equalizer. The plan was simple: send the A-4 Skyhawks in low and fast to smash the tank columns before they could reach populated areas. It had worked before. The Skyhawks were fast, accurate, and experienced. There was every reason to believe it would work again. But the Egyptian and Syrian armies hadn't just brought tanks. They had brought something new, something the Israeli pilots had never faced at scale before. The Soviets had handed their Arab allies thousands of a weapon called the SA-7 Strela-2. NATO called it the Grail. It was a man-pads, a man-portable air defense system. It weighed about 20 pounds. One man could carry it, aim it, and fire it without any training beyond a few hours of instruction. And it was designed to do one thing: reach up from the ground and kill low-flying aircraft. Think about that asymmetry for a moment. A $2 million precision strike aircraft, flown by a highly trained combat pilot, representing years of investment and national capability, brought down by one man lying in a ditch with a 20-pound tube on his shoulder. That was the SA-7. And the Egyptian army had deployed them by the thousands along every approach route the Israeli Air Force would use. The missile was heat-seeking. It tracked the infrared signature of a jet's exhaust plume and steered itself toward the brightest, hottest source it could find. When it got close enough, a proximity fuse detonated the warhead. Now here is the fatal geometry of the A-4, and this is the part that made the SA-7 so devastating against this specific aircraft. Heinemann's brilliant compact design placed the engine exhaust nozzle at the very base of the tail. Directly above and around that exhaust nozzle sat the most critical control surfaces on the aircraft: the elevators, which control pitch, the rudder, which controls yaw, and the hydraulic lines that connect the pilot's inputs to all of it. In a larger aircraft, an engine hit might be survivable. The damage could be isolated. But on the A-4, the exhaust nozzle and the control surfaces were practically neighbors. When an SA-7 locked onto a Skyhawk, it didn't need to destroy the aircraft. It didn't need a large warhead or a catastrophic explosion. It tracked the heat straight to the exhaust nozzle and detonated within feet of it. The shrapnel of even a small warhead detonating at that precise location would shred the hydraulic lines, destroy the elevator linkages, and sever control of the aircraft in an instant. The pilot would survive the explosion. The jet would still be flying, but without hydraulics, without pitch control, the nose would drop and there was nothing the pilot could do. The jet would auger into the desert. In the opening days of the Yom Kippur War, the Israeli Air Force lost aircraft at a rate that shocked even the most pessimistic pre-war planners. A-4s were going down nearly every single day. Pilots were ejecting over enemy territory. Some were rescued, some were not. At that rate of attrition, the Skyhawks fleet had weeks before it would be combat ineffective. And without the Skyhawks hitting those tank columns, there was nothing between the Egyptian armor and the Israeli heartland. They couldn't call McDonnell Douglas and order a redesigned jet. They couldn't wait for a new electronic countermeasure system to come out of a laboratory. The engineers at IAI, Israeli Aerospace Industries, had days, maybe less. They needed a solution that didn't exist yet, so they invented one.
The engineers didn't schedule a meeting. They walked out to the flight line. The logic of the problem was brutally simple once you stated it out loud. The SA-7 tracks heat. It detonates at the source of the heat. The source of the heat is the exhaust nozzle. The exhaust nozzle is surrounded by the control surfaces. Therefore, move the heat. If you could physically relocate the point where the missile detonated just far enough behind the aircraft that the blast radius no longer reached the hydraulics and control surfaces, the jet would survive. The pipe would absorb the explosion. The tail would be untouched. IAI engineers designed a purpose-built exhaust extension, a heat-resistant steel tube engineered to attach directly to the existing exhaust nozzle and extend the outlet rearward, past the elevators, past the rudder, past the hydraulic lines. The thermal plume, the infrared signature that the SA-7 was hunting, now terminated several feet behind the aircraft, instead of directly beneath its control surfaces. It added drag. It disrupted the clean aerodynamic profile that Heinemann had spent years perfecting. It looked frankly absurd on an otherwise elegant aircraft, but the physics were undeniable. An SA-7 would launch, it would acquire the infrared signature, it would track the plume, but now the plume ended in empty air several feet behind the tail. The missile would detonate right there at the tip of the extended tube in open space. The explosion would destroy the extension tube. It would blow the end of the pipe apart completely, but the elevators were untouched, the rudder was untouched, the hydraulic lines were untouched. The pilot would feel a sharp concussion, like being rear-ended at highway speed. He'd check his instruments, green across the board. He'd look in his mirror and see that the back half of his tailpipe was gone, and he would fly that jet back to base, where a ground crew would install a new extension, and he would be airborne again within hours. That single engineering solution, a steel tube, engineered and installed in days, kept the A-4 fleet combat effective at the most critical moment in the war. It didn't eliminate the SA-7 threat. Pilots still had to fly through walls of ground fire, but it removed the specific catastrophic kill mechanism that had been destroying aircraft after aircraft. It turned a fatal hit into a survivable one. In a war where Israel was measuring survival in days, that was everything. The scale of Israel's losses in the first week of the Yom Kippur War triggered one of the most significant logistical operations in Cold War history. Operation Nickelgrass, the American emergency resupply airlift, delivered over 22,000 tons of military equipment to Israel: tanks, ammunition, artillery shells, spare parts, and replacement jets drawn from reserve and storage inventories. It was the largest American military resupply operation since the Berlin airlift, and it arrived just in time. Israel held, the line stabilized, and when the war ended, the Israeli Air Force sat down and made a list of every lesson the Skyhawk had taught them, in blood. The result was the A-4N Ayit, the most capable, most heavily modified Skyhawk ever built, and it started with the tailpipe. The emergency field solution of 1973 was now a precision-engineered factory-installed component on every A-4N that came off the line. What had begun as a crisis fix was now a permanent feature of the airframe. But IAI didn't stop there. The standard American avionics were stripped out and replaced with Israeli-developed systems, advanced heads-up displays, and indigenous weapon delivery computers that gave Israeli pilots significantly better situational awareness and targeting capability than the baseline American versions. And the guns were replaced. The original American A-4s carried 20mm cannons, adequate against soft targets but lacking the hitting power needed against armored personnel carriers and light vehicles that crowded Middle Eastern battlefields. The A-4N received twin 30mm DEFA 553 cannons, nearly 3 times the hitting power, capable of ripping through light armor that the 20mm rounds simply couldn't defeat. The A-4N Ayit became the definitive version of Ed Heinemann's hot rod. While the United States Navy retired its Skyhawks in the 1970s, Israel kept flying theirs. The F-16 took over as Israel's primary strike platform in the 1980s, but the rugged, rebuilt A-4N Ayit continued in secondary strike and advanced training roles for decades after that, finally retiring from IAF service in 2015. 50 years after Ed Heinemann first drew the design on paper.
Today, we talk about air power in the language of billion-dollar programs, sensor fusion, stealth coatings, low observable inlets. The kind of engineering that takes decades and entire national budgets to produce. And that technology matters. It is genuinely extraordinary. But the story of the A-4 Ayit teaches something that the cost-plus defense contractors don't put in their brochures. In October 1973, the most sophisticated air force in the Middle East was being beaten. Not by a rival superpower's stealth aircraft, not by an advanced beyond visual range missile system, but by a 20-pound tube that any soldier could carry on his back. The response wasn't a new jet program. It wasn't a multi-year research initiative. It was engineers on a flight line, diagrams spread on a folding table asking one question: where does the heat go and how do we move it? Sometimes, the difference between an Air Force that survives and one that doesn't isn't a billion-dollar program or a decade of R&D. It's a group of people on a dusty runway at midnight, a welding torch, and the willingness to try something that looks completely ridiculous, because the physics say it will work. So here is my question for you. Is the A-4 Ayit tailpipe extension the smartest, simplest engineering hack in military aviation history? Or does the trophy active protection system on the Merkava tank, which solves an almost identical problem with completely different technology, still hold that title? Let me know what you think in the comments below. And if you want to see how Israel designed an entire tank essentially backwards, sacrificing conventional armor logic to survive a new generation of anti-tank missiles, the Merkava video is right here. Every engineering decision in that tank is as counterintuitive as the pipe on this jet. Hit subscribe. I'll see you in the next one.